This week we have three new lecture series beginning, 3 or 4. And we'll start off with General Relativity by Sukanta Bose. And Shalabh Kumar is the question and answer host for today. So he will be following a similar technique to what I have been doing last week. Okay, Sukanta, over to you.
Okay, thank you, Asim, and good morning, everyone. So it's good to have you all here. I hope everybody is keeping safe and staying healthy. So I'm going to give 3 lectures on general relativity. The first one will introduce the concept of tensors, and I'll also illustrate their meaning through some coordinate transformations. And one of which will be the Lorentz transformation, which I'm assuming most of you would have already seen in a course on special relativity. I hope you can see my cursor. I will actually use my cursor because that will help me draw your attention to specific figures or equations. This is a figure that you may have seen in the past on websites, if not newspapers or other talks. This is not a real image, it's a simulation. It's a simulation of 2 black holes orbiting around each other. These orbits were generated. Of course, here you just see a snapshot. You don't see the full orbit. Maybe in a future lecture, either my colleagues or I will show you an animation that shows these black holes in orbit. But basically, this was a snapshot taken from an evolution by solving Einstein's equations of general relativity. This was able to mimic the gravitational waves emitted by this orbiting binary black hole. And many such waves have now been observed, or many such systems have been observed with gravitational waves now. Gravitational waves, of course, are one of the predictions of general relativity. And among other predictions, gravitational waves go on to verify that general relativity is an accurate theory of gravity as observed in nature. This simulation was produced by the Simulating Extreme Spacetimes Collaboration. All right, so in this 3 lecture course outline, today we'll focus on tensor. Actually, I should have said just tensors. I will perhaps not have the time to introduce tensor derivatives until the next lecture, but the next lecture will be mostly devoted on tensor calculus and introducing tensors that describe space-time curvature. In the 3rd lecture, I will talk about the stress energy momentum tensor. And the context is that this tensor describes the distribution of matter, radiation, their energy and momentum fluxes, shear, and these properties locally determine how the space-time curvature will be at any given space-time point. I will then use Einstein's equations to derive a solution. And this is basically the solution to these equations in spherical symmetry for static geometries. And what we will get is the Schwarzschild solution, which describes, for example, the space-time around Earth or the Sun, or even these distant black holes very accurately. I say very accurately because the Earth, for example, is not a perfect sphere. Neither is the Sun. But Schwarzschild solution is applicable for spherical symmetric static geometries. Okay, so this is another interesting, successful story of the application of Einstein's equation. What you see on the right is again an image you must have seen last year. This is the image formed through radio observations by a network of telescopes. Together, that network is called the Einstein Horizon Telescope, or EHT. This is the radio image of a galaxy called M87. It's a very heavy galaxy in a cluster which is not too close, not too far. tens of millions of light years away. And what you see on the left is a simulation again using Einstein's equations, and of course matter included to simulate matter accreting onto this central object. So, whereas on the previous slide I actually showed you solution to Einstein's equations in vacuum, where these distant stars they just form the background, and the reason you see these ripples is because of the intervening gravitational waves that propagate from this distant binary to us. Actually, no, that's not true. Rather, what's happening is as the black holes go around, they distort the space-time, and therefore the path of the light rays coming from these faraway stars. Okay, so it is the space-time around these black holes that is distorting these distant specks of light. Okay, so here on the other hand, we are actually using matter, the presence of matter, to describe this accretion disk around the central object. Okay, and so we are using general relativity, but with also hydrodynamics to simulate how light will bend, as light emitted by, for example, elements of this accretion disk, and how it will bend around in this geometry of M87 before it reaches us. So bending of light is another prediction of GR. So in the beginning, let me give you a note on my convention. So I will be often using Newton's gravitational constant, this universal constant G, set to 1, and also the speed of light in vacuum C set to 1. But there will be expressions where I will bring them in just so that you are able to track, for example, how big or small a physical quantity is. Then another word on notations. Greek letters such as mu, nu, alpha, beta, they will denote space-time indices. Roman letters I, J, K will denote spatial indices, which means I have to reserve an index for the time variable or time coordinate. So the time index on vector, for example, will be denoted by t or 0. The spatial indices will also be denoted sometimes by x, y, z, or respectively 1, 2, 3. I'll try to illustrate this in the first few expressions until perhaps you get very familiarized with them. Okay, let's backtrack a bit and start with Newtonian gravity. Newton's law of gravity is well known to you, so I will not belabor this except to observe that this Newton's law tells us that the force of gravity is attractive, and it is proportional to the product of the two masses between which you're measuring this attraction, and the square of, and inversely proportional to the square of the distance of separation between those masses. So here, for example, the force due to mass 1 on mass 2 is given by this expression, where r hat is a unit vector radially pointing away from mass 1 towards mass 2. Okay, so the force is attractive, so it's negative of r hat. This actually achieved astounding success by explaining Kepler's laws, which were found before Newton's law. And these laws explain how planets orbit around the sun. Okay, they explain their shape, namely their ellipses with the sun at one of the two foci. They explain how fast the planets move as they go around the sun, or for that matter, now we know, these laws also very accurately explain how satellites, not just the moon, but also man-made satellites, orbit around the Earth. And it relates the orbital period of these satellites to the orbital radius. Of course, there are technical details which I'm not going to go into here. For example, the fact that these are generally ellipses, means that you'll have to be care how you define the orbital radius. but I will leave those things as maybe assignments for you to think about. There are limitations of this theory. For example, Newton's law of gravity would have us believe that signals in this theory propagate instantaneously, which means that if you suddenly could make the Earth disappear totally, then the satellites orbiting it would know about it instantly and would change their orbits instantly. But that is inconsistent with special theory of relativity, right? Which says that any information can at best travel at the fastest travel at the speed of light in vacuum. So, which means that the Earth vanishing, that news should take finite time to reach the satellites. I mean, it should take of the order of about 4 seconds to reach the moon, right? And then only would the moon's orbit react. Similarly, it does not predict gravitational waves, which of course have been verified now. In fact, gravitational waves would be those that information bearer that tells us if the Earth has vanished, or for example, if the sun has vanished, and it would take about 8 minutes for those waves to come to Earth and then change Earth's orbit. So the fact that Newton's theory, so in spite of the astounding success that Newton's theory of gravity enjoyed in a couple of centuries following it, it eventually was observed by astronomers that there was something odd when you try to apply Newton's law of gravity to Mercury's orbit. Remember, Mercury is the closest planet to the sun, and therefore it has the privilege of probing strong gravity, okay? The strongest you can imagine in the planetary system. This is an exaggerated animated cartoon showing how Mercury's orbit actually behaves as it goes around the sun. This is highly approximate, and it's exaggerated so that you understand that the basic effect of sun's orbit that was found by astronomers is that the nearest point of approach of Mercury, which is called the perihelion, where helios in Greek is for the sun. Okay, this nearest point of approach appears to be precessing around the sun. And much of this precision was actually, much of the precision not shown here, but with added effects, was explained because of tugs and pulls by other objects in the planetary system, including, for example, asteroids, near-Earth asteroids, or asteroids in the inner solar system. But about a tiny amount of 43 arc seconds was left unexplained, and various modifications of Newton's law of gravity were advocated to do away with this discrepancy. But they were all ad hoc, and they all had dirtiness about them, meaning those modified laws would break down when people tried to apply them elsewhere. Okay, but eventually Newton's law was replaced by something that was born out of Einstein's insight. One of the questions he had in mind was that whatever the law of gravity be, it has to be consistent with special theory of relativity, which he had propounded some years ago. And what he came up with is the following picture of gravity: that gravity is not a field or a force coming out of that field, but it's actually space-time curvature. Okay, gravity can be felt everywhere. You cannot cancel or shield gravity. So, which was one motivation for Einstein to come up with this picture, that gravity is all pervasive. So, so it should be imagined as space-time curvature. In this figure, we are taking a slice, a two-dimensional slice out of a three-dimensional, spatial volume. Of course, time should be integrated into it, like special relativity taught us. But in this simplification, we are setting it aside. And this shows that the presence of a mass, like the mass of the sun, would create this depression in the space-time curvature, which is what will essentially tell other test particles how to behave as they come close to this mass. Basically, their orbits will bend. Okay, not just that, even the path of light will bend as it tries to traverse the vicinity of sun. And that's because the path of light or massive particles is governed by these depressions in the space-time curvature around any massive object. Okay? So that then, this picture basically tells you two things, right? One is that you have to describe masses. And remember, masses can move, because just because in this picture, this mass appears to be static with respect to you, doesn't mean that to a passenger in a moving car, this will remain static, right? This will in fact acquire a momentum. In other words, space-time curvature should be influenced by not just masses or energy, but also momentum fluxes. And all of these things are nicely captured, again, as known from special relativity, by the stress energy momentum tensor T mu. Okay? I will describe this in detail. So if you're seeing this for the first time, just bear with me. So, but right now, this is just a symbol that captures information about the mass, the energy density, the energy and momentum flux and shear and so on. And the idea Einstein came up with is that this energy momentum tensor should then influence something that describes the curvature, right? That describes the curvature of the space-time around it. And that would be another object. The curvature here is denoted by what is known as G mu nu, or the Einstein's tensor. Okay? So this says that the Einstein's tensor is proportional to the stress energy momentum tensor. Okay, stresses are also captured in T mu nu. The proportionality factor is arrived at by taking the limit of this equation for weak gravity and slow motion, where we expect Newton's gravity to be valid. And so you should be able to derive Newton's law from this equation. And when you do that, then because you know that Newton's law actually has this Newton's gravitational constant big G here, okay? And that big G is different from this G mu nu, okay? G mu nu is the stress energy, sorry. G mu nu is the curvature tensor, a type of curvature tensor, the Einstein tensor, whereas this big G is that universal constant of gravity, okay? So, but the Newtonian limit tells us that G mu nu is proportional to T mu nu, and this proportionality factor is involves the Newton's gravitational constant and the 4th power of the speed of light. I think there is a question, so let me take a look. Yeah, if you have any questions up to this point, you may ask now. Shalab, you may speak up if you see a question, just in case I miss it.
Yeah, sure, I will. So I think there's none, so we can.
Okay, fine. All right, so moving on. Oh, there is somebody who raised a hand. Maybe that person can write in her question. It seems, so I saw a hand up, Shalab, but I don't think.
Now it is not. There's no hand up. No.
Okay, fine. Oh, somebody wrote a question. Let me answer that. Is there, by the way, I would appreciate if the questions are shared by everyone and not just with me. I don't know whether that is possible. But that's because I would like everybody to see the question. But in this case, I'll read it out. The question is there a physical, so question from Siddesh. Is there a physical contact between object and space-time curvature? If yes, does it cause friction between object and mass? Good question. The answer is the space-time curvature is all pervasive. Okay, so these objects are embedded in space-time. So that is how we would describe that contact. So all of us are in space-time. Okay, we are traveling across space-time. If space-time causes friction, the answer is no. It is not dissipative, so we can move across space-time without losing our energy. Okay, so that is what general relativity would tell us. But you will see, I think, more of this as I get a chance to describe it. So, but anyway, keep that question in mind. Let's move on. Please, okay, maybe I'll take one more question before moving on in the interest of time. So, somebody called, I think, Dr. Sengupta asked a question. I think this person is chatting in. If I see the question, I will read it out. But let me keep moving as Mr. Sengupta writes his question in the chat box. So, and other, so once Einstein's theory of general relativity was propounded in 1915, 1916, it did explain the precession of Mercury's perihelion, right? But that itself will not confirm it as a theory, right? Because in the scientific method, any hypothesis first has to explain observations or new observations. And then it has to make predictions that can be verified with observation made after the hypothesis is floated, right? So one of the predictions of Einstein's theory was that that massive objects like the sun should bend light passing in the vicinity of them, such as light from faraway stars. And this bending of light was verified in 1919 by Eddington and his team by precisely looking at faraway stars. And they used solar eclipse in May 1919 to do so. And May last year, we actually celebrated its centenary. And the Einstein Horizon Telescope imaged it, I think, came out in April, so a little over a year ago. So this was just fantastic that this deflection was confirmed to be about the same angle as predicted by Einstein's theory applied to the mass of the sun. Okay, I don't see any questions, so I'll just keep moving.
There is one in the chat box.
Oh, okay. For some reason, the chat didn't show it to me, so let me go back again. What question do you see? I don't know why it doesn't show me the question.
Oh, okay. So one question is, how exactly do we imagine this 2D slice of 3D space? So in your last slide, you showed a like pictorial view of curvature.
Right. Right. Yeah. So yeah, this is again, you'll get to see more of this in this is just tantalizing hints of things to come. But one way of imagining this is that take away the sun for the moment, right? So then you just have flat space-time. And if you already have been exposed to special relativity, you would know that flat space-time is described by the Minkowski metric, okay? And that metric can be expressed, for example, in Cartesian coordinates and time. So x, y, z, and t. And this two-dimensional slice could just be, say, the xy plane, okay? Where z could be the the vertical axis here, and t could be just a moment when you took this snapshot. And now if you, and the point is that there will be a foliation of xy planes, okay, as you vary z. Okay, so for various values of z axis, you will have xy planes. And now if you bring in this mass, it's going to curve these planes. And this is showing one such two-dimensional plane and the effect of that mass in creating curvature in it. Of course, this curvature is not limited to just one plane. It is across planes. But this is easy to visualize, which is why we often show this embeddings. And again, you'll get a better feeling for it in the next lecture or two. Okay, so bending of light and then gravitational waves. This is actually an image from this first published paper confirming the first direct observation, which was of a binary black hole more than 1 billion light years away, right? And with reasonably heavy masses, something like 30 and 36 times the mass of sun. This was observed on, so it's called 150914 because it was observed on 14th September 2015. it was announced to the world on February 11, 2016. These are the gravitational waves in the two detectors, Hanford and Livingston. On the right panel, we actually show the wave in Livingston in blue. The red waveform is the Washington waveform. Okay, a slit in time because there was about a 7 millisecond travel time. Okay, please write in your questions. I will come to your questions in about 10 minutes. And also one had to, I think, do a phase change. Okay, so now I've perhaps given you a flavor for the fact that we will need tensors, like the stress energy momentum tensor. But there is another tensor, tensor to describe Einstein's equations. So let us do some discussion of tensors. T mu nu is one tensor you may have seen, the stress energy momentum tensor. But another tensor you may have seen is the Maxwell's field tensor, F mu nu. If you want to recall the details of it, I'm going to walk you through it because I'm not assuming everybody would be well versed with this. So let us again back up a bit and recall the electromagnetic 4 vector A. Okay, this has space-time components, and now I'm affecting the notation I had introduced on the third slide. Okay, so mu is a space-time index. So the space-time vector A, which is the electromagnetic 4 vector again, it has 4 components, the space-time components, A0, A1, A2, A3, or equivalently A superscript T, then A superscript X, A superscript Y, and A superscript Z. Okay, so this is variously written as follows. This is the same as, in parentheses A0, comma, AK, where AK captures the 3 spatial components, AX, AY, AZ, or A1, A2, A3. This is also equivalently written as A0, 0 for the time index, comma, a vector where this arrow vector represents a 3-dimensional vector. Okay, once in a while, the arrow vector may represent a 4-dimensional vector, rarely so. If it does, I'll try to clarify it. For 4-dimensional vector, I will usually use the bold-faced symbol, A. Or for that matter, for 4-dimensional tensors also, I will usually use the bold-faced symbol, like in this case, F. So F here is constructed from derivatives of the components of the electromagnetic 4 vector, and this is how it is defined. You take, the mu nu component of F, where mu takes 4 values and mu takes 4 values. So in matrix form, this will be a 4x4 matrix, okay? And I'll come show this again on the next slide. But basically, the definition is the following. F mu nu is, you first take the derivative of a nu, okay, nu is this second index, with respect to x mu, where x mu is just the coordinate, a space-time coordinate, minus the derivative of a mu, mu is the first index, with respect to the space-time coordinate x nu. Okay, this is anti-symmetric under the interchange, okay, of mu nu, and that is captured like this. Okay, you'll see more of this on the coming slides. And the Maxwell's equation, so this anti-symmetrization is denoted by these square brackets. Okay, all right. And that's obvious to see because as you interchange mu and nu, you actually flip the sign. And this factor of 2 again is conventional. So when you expand this, then you basically at half times what you see here. Okay, so that half cancels the factor of 2 there. Maxwell's field equations are gotten from, are captured like this. So they are another derivative, another coordinate derivative of the Maxwell field tensor components F mu nu. Okay, and that derivative is proportional to a 4 current J mu. Okay, so J0 is the time component of this 4 current, and J0 is nothing but the current density. Okay, so we'll come to that again in the coming slide. Mu 0 is a proportionality factor, which is the permeability of free space, which can be measured by looking at how much charge density is required to provide a certain field. In spirit, that Maxwell's field equation is like this, where T mu is like my J mu, and G mu is like the contracted derivative of F mu. And the proportionality factor there was mu 0. So gradually I'm introducing the fact that you have actually lived with tensors already. So remember here, there is in fact a summation over nu, because nu is repeated. So that Einstein summation convention also is something I will flesh out in detail in the coming slides. Let me wait for your questions, because some of those questions may actually be addressed in the next couple of slides. So the electric field and the magnetic field, okay, can be described in terms of derivatives of the electromagnetic 4-vector A. And so that perhaps will bring back your intuition on the utility of A. All right. So remember the time component of A, which we call A0, and similarly the spatial part, A vector. So the electric field, this is a 3-vector. Okay, it has components Ex, Ey, Ez in the Cartesian coordinate system. Okay, like this, Ex, Ey, Ez, right? So those components can be gotten from the gradient of this time component of A and the time derivative of the spatial component of spatial components of A. Okay, and similarly, the 3-vector, the magnetic field, is nothing but the curl of A. Okay, and the field tensor F mu nu I introduced on the previous slide can be expressed now that you know what the Ex, Ey, Ez and the Bx, By, Bz are. Okay, so the field tensor, Maxwell's field tensor F mu nu, which you saw here, okay, this can be written in terms of directly in terms of the derivatives of the electromagnetic 4-vector A, but these can be recast in terms of the electric and magnetic fields, which themselves are just first derivatives of A, and therefore F mu nu can be written in terms of those first derivatives or the E and B components themselves, like this. Okay, you will notice that this is antisymmetric, meaning this is the diagonals are all 0 as expected of antisymmetric tensors. Okay, so this one is F00. Okay, the time component of y. This one is Fxx, Fyy, Fzz, or equivalently F11, F22, F33. Similarly, this component is F01. Okay, that is because the first row is the time row and the second column is the x column, right? So F01 or equivalently Ftx is Ex by c, the speed of light in vacuum. And similarly, F02 is Ey by c, and so on and so forth. And again, the antisymmetric nature is clear because Fx0 or F10, okay, is the negative of F01. And similarly, if you look at this, F2, I should be careful. Yeah, this is F21. F21 is the negative of F12, and so on and so forth. The Maxwell's equations, which were so nicely couched in a form like this, if expanded in terms of the electric and magnetic fields, they will give rise to these equations that again you're familiar with, right? For the divergence of the electric and magnetic fields, and also for the curl of the electric and magnetic fields. And you notice that the source terms also come in. Rho is the charge density, which is J0. And here the bold-faced vectors, I'm sorry, are 3-dimensional vectors, okay, with only the spatial component. So J here is the spatial current. Okay, now let me pause and take your questions. Okay, so from Dr. Varsha Tyagi, the question is it possible that the space-time below a mass is curved but is not curved above it? Okay, so the curvature around an object can vary. Okay, if that is your question, then that's the answer. But it is unlikely that it will drastically vary as much as that it is, say, strongly curved on one side and has flat space-time on the other side. Okay, chances are that if your mass distribution or your stress energy momentum tensor distribution is continuous, then the space-time curvature around it will also be continuous. Okay, and mathematically it has to be differentiable. So those are the properties you would expect it to have. The other question by Dr. Revant is, you have just mentioned that massive objects bend light around them. Then in the parallax method, we might be looking in the wrong direction, especially if there is an object. And yes, your answer is absolutely, sorry, your question is absolutely right, that when you're measuring distances to faraway objects using parallax, if there are intervening masses, they would bend light. So, for example, yeah, this is a form of lensing, like weak lensing, or there are various types of lensing, but I'm not going to go into that right now. But indeed, lensing is another prediction of general relativity. But yes, there will be bending of light, and bending of light will can create these kind of distance measurement errors. So, so we are aware of it. Indeed, for faraway objects, we have to correct for these lensing effects. That's another big field in itself. Maybe some cosmology talk here will tell you some details about it. But in the case of nearby objects, such as for stars within our solar system, if, for example, the sun is coming in the way, right? And that's difficult because in daytime it's difficult to observe faraway stars. But it may still be possible to observe some, say, radio phenomena. And radio waves are also affected by the gravity of the sun, and so sun will have an influence, right, or bias your measurement of the distance. But which is why it is important that 6 months later you come to the other side of the sun, but you still observe the same part of the sky to see what effect the sun introduced in your measurement. But the nice thing is that for the sun we have modeled it, so we can actually subtract it from our measurements, without waiting for 6 months. Okay, sorry, let me. Yeah, I'm having some problems navigating. Okay, through the chat box. All right, and then from Dr. Mehta, the question is how we infer that gravitational wave is from certain source. There will be a few lectures on gravitational waves, so I will let that professor answer it. But I'll give you a snapshot. The way to do that is actually use multiple gravitational wave detectors, so that you can use triangulation. Basically, you measure the time delay of the arrival of gravitational waves at these different points, say across the Earth, right, on the globe. And from by measuring these time delays, you can triangulate and find the direction in the sky. So, but direction is only one part, right? How do you get the distance? The distance can be gotten by measuring the both the phase and the amplitude of the gravitational waves. Okay, because the amplitude itself is influenced by how massive these black holes are, for example, but also how distant the source is, right? So the amplitude is large when the source mass is large, but the amplitude is small when the distance is large. So there is a degeneracy between, say, the mass and the distance. There are other degeneracies which I don't have time to go into now. But so how do you break the degeneracy between the mass and the distance to the source, influencing the amplitude of the wave? You do that by measuring the phasing of the waves, because how the frequency, the instantaneous frequency of the gravitational wave changes with time depends on the mass of the source. So by measuring this phasing, you can measure the mass. You use the mass and the amplitude to get the distance out. Okay, and then the third question is from Dr. Bhatia. Sir, why is time component denoted by 0 and not t? That's just a choice. As I said, we have to get used to the fact that x, y, z can also be alternatively denoted by 1, 2, 3. The reason is simple. I mean, sometimes when you write summation, it's easy to write summation k or summation mu is equal to 0, 1, 2, 3, or mu is equal to 0 through 3. Okay, so that's one reason. Because and then sometimes you worry about permutations of these indices. So when you deal with those facts, numbers maybe give you a little more facility. So it's just a choice. There is nothing sacrosanct about denoting the time index t with 0 or the space index x with 1. Question from Dr. Umang Kumar is, sir, how exactly does a massive object curve space-time? Okay, patience. That is how it curves it. You'll have to wait for the 3 lectures. I'll come to that. There are a bunch of questions that I will let Shalabh, can you please streamline these? I'll take these questions because I noticed that many of these questions are actually about things I'm going to talk. I've not talked about them yet. So please, thank you for asking them, but we'll come to them eventually.
Sukanta, can I just interrupt? I
Yes.
think if people have been writing to you, then Shalabh will not be able to view those questions.
Yeah, please, if you have written to me, I've already alerted you in the past. Don't write to me privately. Write these questions directly to, Asim, you want to say to everyone or to Shalabh?
No, to Shalabh. They should write
Yes.
to Shalabh.
Yeah.
Yes, please copy and paste your questions to Shalabh, and he will be the moderator because there are just too many questions, and it won't be fair if I answer, pick two of you arbitrarily.
And just one quick thing, people are asking whether you will be sharing your slides. We have a provision to make the slides available to the participants.
Yeah, that will be, yes, I plan to do that. Yes.
You can just send them to us.
Yes.
Okay.
All right, very good. So moving on then. So we saw a nice example of how 4 of these Maxwell's equations can be couched in a simple expression that is tensorial, right? Which is this equation. It's written in terms of the field tensor and is proportional to the a source term, which is basically the electric, charge density and current. And an example of the Einstein summation convention is illustrated on this slide. So, this form of the Maxwell's equations, you notice that I mentioned that there is actually a summation over this repeated index nu. So what does it mean? It means that nu will appear only, summed over all values of nu on the left hand side. It will not appear on the right hand side. Okay. In fact, the free index mu will appear on both sides. So let us take an example where mu is chosen to be the time index, say 0. Okay, then the mu on F will be 0. The mu on J, the current, current will also be 0. So you will have from this equation on the left hand side that the x nu derivative of F0 nu, where there is an implicit summation over nu going through 0, 1, 2, 3, right? That when expanded, so this is all just the left hand side, okay? This is just dealing with the left hand side. This means, this thing here means that you have to sum over all values of nu, meaning the first term will be 0, 0 for nu. And then you sum it with another term when nu in both places is 1. And then you add a third term where nu in both places is 2. And then finally a fourth term when nu in both places is 3. So this is called the Einstein summation convention, which means that when an index is repeated, okay, in the superscript and the subscript, then it is implicit that there is actually a summation. Okay, imagine there is a sigma here, where the summation is from nu equal to 0 to nu equal to 3. And when you explicitly write out that sum, you get this expression. Okay. Now, if you go back to now, but we want to test whether this indeed gives me, mu 0, j 0, right? How do we do that? You go back, or rather, this should be the divergence of E, right? Because this is actually that time component of Maxwell's equation. So do we get this equation? The fact is that if you now look at what F00, F01, F02, F03 are, then from the definition of the field tensor, you notice that they are just 0, Ex by C, Ey by C, Ez by C respectively, right? So you take the 1 by C out. The first term was 0 because F00 is 0. The remaining 3 terms give you these 3 derivatives of the electric field components. But these are the, respectively X derivative, Y derivative, and Z derivative, which is nothing but the divergence of the electric field and with the 1 over C outside. And indeed, this is what we have on the left-hand side of the Maxwell's field equation, except for the 1 over C. But 1 over C, when taken to the other side, will give you C in the numerator. And C, right. So this quantity is mu 0 j mu, right? But j0 itself is C times rho. Okay, we know that because you will notice that if you take this c to the other side, you'll get 1 over c squared, but 1 over c squared is just mu 0 epsilon 0. So the mu 0 on the left-hand side will cancel the mu 0 on the right-hand side, and you will just get divergence of electric field is rho divided by epsilon 0, right? The permittivity of free space. So this equation actually checks out. So we just verified that the time component of the 0 component, or basically setting mu equal to 0 in this Maxwell's equation, right, does give you the first law of Maxwell's equation, which is that the divergence of the electric field is rho divided by epsilon 0. Okay? And by the way, you can actually write it in another form. So to get some more familiarity with tensor manipulation, right? This is Maxwell's equation, but now let me substitute for f mu nu the definition, which was that anti-symmetrized derivative of A, right? Okay, there is a, yeah, this is fine. So this is what you actually get if you write this out. Okay, I will let you verify it. So when you substitute for f mu nu, going back, okay, this is the expression I'm going to substitute, and then you have to manipulate your symbols a bit. But when you do that, you can verify. Basically, what happened is that when you expand this, you get the derivative of a nu with respect to x mu, but there was a derivative of x nu outside. I just swapped those derivatives. I just interchanged those derivatives. That is how I got this x nu derivative inside and the x mu derivative which came with f mu nu outside. But that's just playing with terms. So this is the form in which you can write it, and then this form can be redefined as this D'Alembertian acting on a mu. Okay. So this is another thing I will let you work your heads through. Okay. Basically, what is happening is the following. You can let's see. So this is a mu, and then there is a summation over nu here, which is fine. Right. And then there is this derivative. But this derivative, I'm claiming that you can make a transformation to get rid of this derivative. Okay, this derivative is nothing but the four divergence of a nu. Just like you have this 3 divergence, right? Just like you have this 3 divergence of the electric field. Okay, here these are all 3 vectors. Similarly, you can have a 4 divergence of a nu, because nu here is summed over 4 indices, space-time indices. Okay, I'm claiming that you can choose a gauge so that this quantity goes to 0. Why is that? Because you will find that going back, this electric field and magnetic field, they remain unchanged if you change the 4 vector A by a transformation like this. If to that 4 vector you add the derivative of some scalar lambda with respect to x mu, right, to get a new vector a mu prime, then you can verify to yourself that your electric field and magnetic field remain unchanged. Okay, and these are the physical variables which you measure, which is why this is called a gauge transformation. That any such transformation of your electromagnetic 4 vector will leave the electric and magnetic fields unchanged. Okay, and now we are not worried about quantum mechanics and effects like the Aronoff bomb effect. Okay, if you want to look at them and see the effect of such physical effects of gauge transformation, then do study it on your own. But here I'm just looking at classical fields. So this kind of a transformation is called the Lorentz. This is a different kind of Lorentz transformation with no t. Okay, so L-O-R-E-N-Z without a t. So this kind of a transformation allows you to choose a lambda so that the 4 divergence of A vanishes. In other words, if you take the 4 divergence of both sides, you can choose lambda so that the D'Alembertian of lambda cancels this divergence of A, so that the new divergence of A mu prime is 0. So then you're left with this equation. So this is the D'Alembertian, okay, this x nu double derivative contracted over nu acting on a mu, and this negative sign can be taken to the other side, giving you minus mu 0 j. Okay, this D'Alembertian is indeed this double derivative contracted over space-time indices, and it has time component, which is this one. The reason there is a negative sign is because the Minkowski metric component G0 or eta 0, 0 is -1 in my convention. Okay, eta 1, 1, eta 2, 2, eta 3, 3 are all positive ones, and that is what gives you this Laplacian in 3 dimensions. Okay, so that is how I get another tensor equation. Now this D'Alembertian acting on a mu being proportional to the 4 current J. Now with this introduction, let me introduce a coordinate system, because as you just got a flavor for, for the electric field and magnetic field, we do need coordinate systems to calculate things. But eventually, to compare observations between 2 coordinate systems, okay, or 2 labs, one in a room, other in a car, right? We need to know how the different components of, let's say, the electric field, right? They will transform from one coordinate system to another coordinate system, where one of the coordinate systems will be denoted with the alpha index. The new one will be denoted by the prime index, say alpha prime. So alpha prime could correspond to an inertial frame S prime, which is maybe a car, okay, moving at a constant velocity. But S prime is moving with respect to what? It's moving with respect to, let's say, the room in which you're sitting. Let's call it S, okay? So let me go over this once again. Since we are dealing with space-time vectors, such as a mu on the previous slides, right? It's good to have some basis coordinates or basis vectors. So any space-time vector A can be resolved in terms of 4 space-time basis vectors. Okay. Usually in Euclidean geometry, you have used 3 space vectors like x hat, y hat, j, k hat, or sorry, x hat, y hat, z hat, or equivalently I hat, j hat, k hat. Right. Here, instead of I hat, j hat, k hat, I will have E1, E2, E3 vectors. So again, 1, 2, 3 are denoting the x, y, z components. But in addition, I'll have this 4th basis vector, E0. So, and these are all local, okay? These are defined at any given point in space-time. So let us say you have coordinatized your space-time with some grid, okay? So at any given point, I would say then that E0 only has time projection. So it has unity, and these are unit normal. So it has a component of unity along the time axis, and it has component zeros along the x, y, z axis. E1 similarly is 0, has 0 components everywhere, meaning all components are 0 rather, except for its x component, okay, which is 1. And E2 has only the y component unity, and E3, which is basically the unit vector along the z direction at a point, has only the z component unity. Other components are 0. So that means that okay, in the past I was using A as my electromagnetic 4 vector, but now A can be any 4 space-time vector. Okay, so my 4 vector A can be resolved in terms of these basis vectors very simply like this. Here again, this is the next instance of using the Einstein summation convention. Okay, I see people asking questions. I'm almost done. So, well, I'll take about 3 minutes and then end and take your questions. So here there is Einstein summation convention, which means what I have not written is explicitly is a summation over the index mu, where mu takes values 0, 1, 2, 3. But when I apply it, I get this sum over those 4 terms, where first mu is 0, then mu is 1 in both places, and then mu is 2 again in both places, a mu and e mu, and then finally mu is 3 in both places. That is on A and in B. Okay, so this is again reminiscent of what you do in Euclidean geometry, right? You often write a spatial vector like the electric vector in terms of ex, I, ey, j hat, and then ez, k hat, right? So this is basically like that, but now you also have a time component. Okay, so A0, E0 vector. For the electric field, it actually doesn't make any sense to have a time component. And that is because the electric field or the magnetic field are not 4-dimensional space-time vectors. And that's a problem, as you'll see in a moment. So, but for this electromagnetic 4 vector A, it is actually naturally a 4 vector. And thankfully, the 3 vectors, E vector and B vectors, can be derived by taking appropriate derivatives of the vector A. Okay, now under a coordinate transformation, and this is a very key insight, so keep in mind. The key message here is that under a coordinate transformation, the 4 vector itself does not change. Okay, A does not change. A is a vector which doesn't care who is measuring it. It just exists. You know, if there is an if there's a current distribution that has produced a certain A vector at any space-time point, then it exists like that. You may measure its components differently. For example, if you measure its components A0, A1, A2, A3 in your room, you may measure them to have certain values. But the vector itself will not change if it is measured by your friend moving at a high velocity in a car. What changes are its components. So that is why I don't change A, but I denote its components in the moving frame S prime as A mu prime. And the moving frame will have its own coordinate system, because your moving friend will make measurements in his lab, which is coordinatized by another set of coordinates and Cartesian grid and so on. So we call that coordinate system E mu prime vector. Okay. So by the way, this is an example, and sorry for this mixture, but here the vector denotes 4 space-time vectors. Okay. So I'm explicitly clarifying it. So when you expand this, you get A0 prime, E0 prime vector plus E1 prime, A1 prime, E1 prime vector, and so on and so forth. All right. So notice here that the basis vectors are different because these basis vectors are fixed to the moving car. And similarly, the measurement of these fields, A, right, produced by the same charge current distribution. Okay, the charge current distribution is the same, the vector A is the same, but its components are now measured in the moving car, and they will be different. Okay, so for example, how will they be different? One way to do that would be to connect them with the Lorentz transformation, right? So let's say there is a Lorentz transformation defined by this matrix. Okay, that relates the frames S and S prime. Okay, here the velocity of the moving car has a magnitude V, right? And gamma, this boost parameter, is related to V square like this. It is just 1 divided by a full square root over 1 minus V square. Okay, then this 4x4 matrix, this space-time matrix, the Lorentz transformation matrix, is symmetric and is given by this. Here, the velocity is along the positive x direction. Okay. This matrix allows you to relate how the new components, A nu prime, will be in terms of the old components, A mu, okay, measured in your fixed room. Okay, this matrix, this Lorentz transformation matrix will tell you how the space-time components of the electromagnetic field vector A, measured by your friend in the moving car, will relate to the components that you measure in your fixed room, okay, in your room fixed to the earth. So you can expand this because here mu is summed over. So you just choose nu prime to be 0, and then when mu is 0, then this 0, 0 is gamma. So the time component in the moving car of A is just gamma times, and this will have to be summed over. So there will be 2 pieces. It will be gamma times A0 minus this second terms, okay, minus V gamma times A1. Okay, this is how the time and x components will get mixed. You know this from the Lorentz transformation of coordinate systems, right? So, but using this, then you can figure out how the basis vectors will transform. Okay, so this is something I will go over next time with you. But today I will ask you to read up about Lorentz transformation from any special relativity book you have, or even online. Okay. Bernard Schutz's book on first course in general relativity is one of the references I'm using. So that is another book you may use. Okay, Bernard Schutz, general relativity. I think Shalab can write it in the chat box for everyone. Okay, let me stop here and take questions. So yeah.
So there are some questions which I have shortlisted.
Okay.
Because some of them are relevant for this lecture and others are for the next lectures.
Okay.
So, the questions which I'm going to ask on behalf of the participants are basics. Like one question is, what's the difference between vectors and tensors? from
Okay, let me answer it right away. Vectors are an example of tensor. Okay, tensors can be of many types. Very soon, so in the next lecture itself, I will actually tell you that vectors like the ones I introduced, they are just one type of tensor. Okay, there are other types also. You'll come to that next lecture. Next question.
So yeah, some person was asking references for vectors and tensors. So
Again, I would say Bernard Schutz's book on first course in general relativity, but you also have Jent Narliker's book, although it uses somewhat old approach. But for understanding vectors and tensors, you can take a look at that. There are many other online resources, so I will not necessarily ask you to go ahead and buy a book right away.
yeah, even on Wikipedia they can study. I think.
Yes, even on Wikipedia you can have a. So if you look at Lorentz transformation on Wikipedia, there itself you will have some links to what vectors and tensors are.
And one question is, are the space-time physical or mathematical entity?
No, space-time is a physical entity, and we use mathematics to describe phenomena on space-times. Okay.
Okay, so there are few hands raised. So I will enable unmute one.
Okay.
Junik, you can ask.
Hello, sir. Good morning.
Yes,
Sir,
go ahead.
actually, I got a question which was from the beginning time of the lecture that you started. Sir, on the beginning, when you were explaining those assumptions, just before you started, we were explaining some assumptions which we have chosen before proceed. So on there, you just said, yeah, in this slide, you just said we said G is equal to 1. That was clear. That part was clear. But from what point of view, we are also choosing the velocity of light C also to be 1?
This is just a system of units, right? You can choose a system of units where your answers will be expressed in terms of G and C. So therefore, you can set it. You can set G and C to 1. Let me give you an example. I've not used it today because it was new, but you look at this Einstein's equation, right?
Okay, sir.
Now you look at the proportionality factor, which is 8 pi times G over C to the 4. Now, in SI units, G is some 6.67 times 10 to the minus 11. C is some 3 times 10 to the 8 meter per second, right? So you can immediately see that G over C to the 4 is a very small number. And understandably so, which is exactly why it takes a big Earth to create enough curvature to keep you, stuck to the Earth, right? And that is because gravity couples very weakly. I mean, the Earth's matter distribution produces a very weak gravitational field, right? And that is because of this fact, G over C to the 4 is very small. So if you use SI system of units, this factor will be very, very small. Okay, but if you express everything in terms of a unit where, it's not meter per second or something like that, but it is G over C to the 4, then the value of this proportionality factor is just 8 pi. Okay, because the system of units you're using there, 8 pi is being expressed in terms of G divided by C to the 4. That's another way of saying is that I'm setting G is equal to 1, C equal to 1. So these are called geometric units or geometrized units. So when G is 1, C is 1, then this proportionality factor is 8 times pi. Another way of saying that is that the proportionality factor is really 8 times pi times, G divided by C to the 4. Just like we say something is 8 pi in, units of meter per second, that kind of thing. It's just a system of units that we are choosing the moment we say that, I'm setting G equal to 1, C equal to 1. So with practice, you will be able to tell that, yeah, okay, this is what I'm setting. And I'll show you more examples in coming lectures. What else?
There's one question from YouTube live streaming.
Okay.
It is, why do we take this Newton's constant G in Einstein's equation?
As I told you, it comes from observations, right? Without observations. So that's another reason somebody asked, space-time is real or mathematical. The answer I said is space-time is real. The effect of the space-time of the sun, right, around the sun, on the planets is actually measured, for example, by how the planets are moving as they fall around the sun, right? all the planets are trying to do is they're trying to maintain as straight a path as possible, but in this curved space-time. And that is what is making them keep falling around the sun. And they're basically traveling the straightest possible path, also known as geodesics, around the sun. And I'm going to introduce geodesics, time permitting, in a couple of lectures. Now, so coming to your question, yeah, what was the question again?
So why do we take this Newton's constant G in Einstein's equation? Why do we multiply it?
Right. So coming to your question, so by making measurements, right, such as the force of attraction between two masses, remember that attraction is explained by this law as well. It is just explained not in terms of force, but by saying that, okay, this mass curves this mass is described by T mu nu, the stress energy momentum tensor of this mass. It curves the space-time around it, but how strongly it curves the space-time is determined by G. If G was much stronger, then the curvature here will be much stronger. This depression will be much faster and deeper, right? For the same mass. So this G, this Newton's constant, actually comes from measurement. And that was measured even to verify Newton's, or to go with Newton's law of gravity. Okay, so G is a very physical quantity, and it comes from measurement. Because we already knew it from Newton's law, as I said, if Einstein's equation is the correct theory of gravity, then under certain approximation, it should go back to Newton's law, because Newton's law also describes natural phenomena pretty accurately. I mean, Newton's law is quite sufficient in projecting trajectories of satellites around the Earth. Okay, and so from measurement of those orbits and the mass of the Earth, you can actually tell what G is. Let me introduce also another fact. General relativity does become important even for these orbits at some level, and that is because general relativity from these equations actually tell us that the rate at which clocks measure time on the surface of, let's say, the Earth here, for a moment I'm considering this as Earth, and at a satellite there is actually different. Okay, and this time dilation because of gravity is something, again, you will see in Schwarzschild when we discuss Schwarzschild solution. And if one does not correct for this time dilation, then one will actually not be able to keep the clocks synchronized. And that in turn can result in inaccurate measurement of distances using the global positioning system, GPS. Okay, maybe last couple of questions, if there are any.
So one more question from our YouTube live streaming, that you talked about only Mercury perihelion in the introduction. Why not the perihelion orbit of other planets like Venus, Earth, etc.?
Yeah, I actually answered that very briefly when I said that that is because the precession of Mercury's perihelion is the largest of all the planets. And the reason for that is that Mercury's perihelion accesses Sun's gravity most deeply among the planets. Of course, you can broaden this discussion to include asteroids, etc., that perhaps come even closer. And then there are ways of tracking their orbits and checking whether Einstein's equations are right in a field where gravity is stronger. In fact, nowadays we do it with black holes, right? When we look at the orbits of black holes, they actually are able to sample much stronger gravity, and we are able to check Einstein's predictions in much more stronger field. Okay, much stronger field, and that is important because after all, Einstein's gravity was determined to be a more accurate theory than Newton's theory by probing strong field gravity. So the next frontier for testing gravity, in this case Einstein's theory, would be to take these experiments to places where we have stronger gravity than suns, and such gravity exists around these stellar mass black holes. Okay, anything else?
I think that's it for today's lecture. There are some other questions which I think are more relevant for the next lecture.
Yeah, I will quickly answer a couple of questions from the chat so that people don't feel disappointed. But please, many of the questions in the chat actually are about aspects that I'm going to discuss in the next couple of lectures, which is why I'm avoiding to answer them. But people asked about whether electric and magnetic fields bend space-time. So the answer to the question is. You can imagine a black hole with an electric field. Then indeed, the way that charged black hole will bend space-time is going to be different from how a electrically neutral black hole bends space-time. So in that sense, yes, these field distributions have an effect. Okay, they can come in ultimately through T mu, so they have an effect on space-time. Number two, there was another question about the Maxwell tensor and permeability and permittivity. There I would say, once again, yeah, please look up Wikipedia or any other textbooks such as Griffith's or Jackson's to maybe refresh your knowledge about Maxwell's equations, and then go back and check these slides to come up to date on how those equations can be cast in a tensorial form. Okay, and then maybe, yeah, there were many questions about gravitational waves. Like when gravitational waves are produced, is the energy of the object decreasing? The answer is gravitational waves do carry away energy and momentum, so that has to decrease somewhere, and it could be such as from the orbit. Okay, so if you're worried that okay, how can anything come out of a black hole? The answer is no, nothing is coming out of the black hole. But if you take two black holes, as they orbit, they will fall in, and that falling in this gravitational potential, so to speak, is compensating for the energy that is, or providing the energy and momentum that is then lost in gravitational waves. There was another question again on what is the difference between vector and tensor. The answer is vector is a special example of a tensor. There is no difference. Tensors are a broader category. Like stars can be of many types. Neutron stars and black holes are two types of stars, dead stars. But stars are more general. So similarly, tensors are more general, and vectors are only one case of tensors. I think, yeah, what I'll do is I'll take a more complete look at all the questions in the chat, and I'll try to have anything I have not answered today prepared as answers next time. Okay. In the interest of time, and I know the next lecture is on our heels, so I'm going to end now. But thank you for your questions.
Yeah, and I will request all the participants to write the questions to me rather than Professor.